guidelines, do let me know. I try to be as specific as possible so that, you know, we all have numbers that we can compare between the various technologies that you have all proposed. But I also try to keep it a little bit more general because of the heterogeneity of the topics that you all have proposed. So if there are any questions, do let me know. And then of course the peer review will occur after that. Then we have a huge jump in the dates before we get to our next assignment, which will be due on a Monday, not on a Friday. I emphasize this to bring it to your attention because it's not within the usual cadence of assignment due dates. So just be aware of that. And I purposely put a lot of time in between sustainability and the work plan assignment because obviously the work plan is going to be the culmination of all the other assignments that you've already been working on to put together, you know, a cohesive plan that tests, you know, your hypothesis and build upon what your late review has done. And I anticipate that your list of references will also grow as you work on your sustainability assignment and then your work plan as well. So I will be pushing out those guidelines for the work plan sooner rather than later because I want to give you all the maximum time possible to really think about, you know, how do you formulate a research plan within, you know, a reasonable period of time. And typically you want to think about timelines that are about 3 years because that's, well, one, the typical NSF proposal timeline, but also that's enough time so that you can test out what you need to test out, but in long enough, you know, that you can have the time to do the work, but short enough so that it's not dragging on and on before, you know, you have to make some critical decisions about the project. So, but that's coming down the pipeline. That's also after spring break, so I won't be seeing you for some. I mean, I'll be here, but just not in this group. Is what I mean. So that is that. Any questions thus far for those starting in assignment? Alrighty then. Let me just close this a little bit. Oh, I also want to mention for everyone to keep your eyes peeled for things that are coming down the pipeline. So after our modules on sodium ion and lithium sulfur and well, conversion and alloy materials, we'll be getting into interfaces as well as discussion of like materials characterization. Now, there's a lot to talk about for those two topics alone. In fact, we can have a whole semester just discussing interfaces, really, right? And so what I want to do is to down select, but really tailor it to this audience, as we've been doing anyway, right? So, so I'll be sending out a poll to sort of see, you know, not only research interest, but also just general educational interest, because just because you're working on, you know, lithium ion or sodium ion or anode, that you're not curious about some other family compounds or methods. You know, so I want to see, you know, what overlapping themes there are in terms of interest from the group, and I'll down select from there. I mean, I think I have a pretty good idea, but you know, I will let the data guide me. And maybe confirm what I already know. So, so I'll be sending those out and the questionnaire out. So look out for that, and then we can go from there. I dedicated 3 weeks to materials characterization, but we can play it by ear. You know, we can, you lengthen solid, we can lengthen interfaces, solid electrolyte interfaces, electrolyte interfaces a little bit more if there's more to cover there, or less, depending on what the data suggests. But we'll go from there. Okay. Rightio. All right. So sodium ions, we were several slides into this module already, so I'll just recap. We left the discussion of sustainability. We discussed in depth about how components within a sodium ion battery would be different than that of lithium ion batteries. We also compared, in terms of direct cost comparison, is it really one-to-one? Are we really just subbing out sodium, subbing out lithium for sodium ions? A little bit, but obviously the chemistry is different. And then we discussed sustainability in terms of, we can sub out copper current collector for aluminum, thus cutting down the cost, even if we have to increase the thickness a little bit, 50% when we use aluminum versus copper. So, there's certainly a lot of advantages when it comes to costs and manufacturing for sodium ion batteries, but the cost savings, we talked about, isn't so extreme that it is the main driving factor. Just because of the earth abundance of sodium does not translate to a direct, significant cost savings when you go from lithium ion to sodium ion batteries. And in fact, for some fictitious averaging of cathode materials that are in the future for sodium ion batteries, the overall cell manufacturing cost is actually slightly more. Not significantly more, where it's like where basically it's a non-starter, but it is not that huge of a cost saving. In fact, it's more. So, so now we started talking about sodium ion battery materials and really appreciating the rich history of sodium ion battery materials. And this is going to be the theme that you will see in the discussion of not only sodium ion batteries, but also lithium sulfur batteries and alloy anode materials. There's a huge, very rich history, since the 60s and 70s of work that have been done on all of these materials. And the resurgence is obviously renewed interest. The resurgence in scientific work that's done in these areas are due to renewed interest because we are at a very critical point in terms of climate change, and reversibility of global impact of climate change. So it's not that these materials are new per se. We have new understanding. We have maybe higher resolution characterization techniques that really enable us to tease out certain mechanisms that maybe we didn't know before, repurpose some of these materials for certain applications that they weren't looked into before, right? Like NASA was looking into iron air for obviously shuttles back in the 1960s, and now they're for grid storage, right? So, these materials are coming back, but we should really appreciate the work that's already been done, because a lot of the work has been done in like molten salt batteries that we could try to tease out and try to apply to some of the applications that we have now, like room temperature. Do the mechanisms translate? Sometimes the answer is no. Molten salt mechanism is obviously absolutely different than when you're talking about room temperature application, but there's still a lot of chemistry that's already established there that we can appreciate and build upon. And I'm going on this rant because I want you all to appreciate that the foundation has been set, and we should build upon that as opposed to buy into the hype that these materials are new. There's so much work on sodium ion batteries through solid electrolyte discovery, like beta double prime alumina. right? That we should really build upon that, understand the material structure and the properties so that we don't buy into this hype that like, sodium ion is like new. It's actually quite old work. Okay, so we left off here talking about the benefits of beta double prime alumina consisting of this solid solution of sodium oxide and alumina with the ratios of X going from 1 to 1.6. So you see here the diffusion coefficient is extremely high for that of sodium ions relative to other monovalent cations. Okay, so that has attracted, and the technology has been commercialized. It's quite mature, right? I mean, there are some flammability issues, and in fact, one of the seminar speakers in the material science department a few weeks ago has pointed out what we've already heard about in the popular press, which is there are these grid storage deployment of the grid storage buildings where sodium sulfur is housed in, and sodium sulfur batteries are housed in. But you see the operating temperature to get it to the molten state, right, is 285 C. And so operating at these high temperatures, once you get your batteries up to these high temperatures, the thermal management, keeping it at that temperature is less of an issue. Keeping it safely at that temperature and not causing runaway thermal reactions, that's more of the issue, right? But in terms of deployment and the applicability and where these things are used, they're already out there. And the Zebra batteries have also been in use as well, using earth abundant materials. So there's a rich history of sodium ion battery development already there, but they weren't specifically called sodium ion batteries. They were called molten salt batteries. So in terms of looking in the literature and comparing, some terminologies have not changed, but different areas for these materials were used. Okay. Right, we already discussed this, so I won't belabor the point in terms of going into repeating these details, but certainly there are, in summary, enough similarities between lithium ions and sodium ion and transporting these ions within a battery that we can really glean from what we know about lithium ion battery technology to sort of apply that to sodium. Now, the differences, of course, is where is what requires a lot of the work. And it really comes down to the fact that you're trying to transport an ion that's just much heavier, okay? 1. 2, that means the crystal structure of your material, it's heavier and it's larger. So the kinetics and the crystal structure of the materials, the host materials, are just going to have to change, which one will, of course, change the chemistry of the cell, okay? And so then you think, okay, well, that's not too bad, except it is, because now you're just in a totally different regime, right? So we started talking about layered structures, and you look at some of the compositions for layered sodium ion battery materials, you see that there are some similarities, right? So for the compounds with high capacity and also high average voltage of the cell versus sodium plus, you see that the layered materials, you recognize some of the compositions, they're similar. So you have here P2, sodium 2/3, nickel, manganese, titanium oxide. You also see some sodium cobalt oxide with half substitution with iron. So there are some similarities, but the chemistry is actually quite different, and how these materials, how these compounds restructure upon sodiation and desodiation are quite different than that of lithium ion batteries, right? So that's what we'll focus on, is like, how are they actually different? And how does that benefit and also limit the use of sodium ion batteries? So this is where we left off. We left off discussing the layered structure itself. So in comparing with the lithium-ion analogs, right, we have lithium cobalt oxide. So in comparing sodium metal oxide, so NaMO2, we talked about depending on where the sodium ions sit, that results in different crystal structures. And you can access these structures not just electrochemically. You don't have to just be out of equilibrium. You can actually synthesize these starting materials in the O3, the P3, the O2, the P2. But it requires also a little bit of subtlety. It's not so much that, well, I should rephrase. You'll see when you synthesize these materials that you actually have to control the amount of sodium that goes into the starting material, the starting composition, because that will allow the initial crystal structure to be, O3 or P2. So the names are pretty self-explanatory. So if the sodium ions are sitting in octahedral sites that you see here in this layered structure, where this is the metal oxide, and then this is this layer in which sodium ions will occupy. If they sit in octahedral sites that you see here, then it is an O3 type structure. But then if the sodiums are sitting in the prismatic structure or prismatic site that you see here, then it'll be denoted as a P3 site. Okay, and so when sodium ions go in and out, through insertion and deinsertion, they can actually then start to also occupy other sites, and then you'll have rearrangement. The rearrangements will allow you to go from O3 to P3. Okay, so already you're seeing differences from sodium ion battery cathode materials and that of lithium ions, right? Because we haven't discussed these prismatic sites in layered lithium ion battery cathodes. So, ultimately what you want to know is how do these materials behave as electrochemically? When you start to desodiate and also then resodiate, how does this affect rate capabilities, and also how does it affect capacity? Well, from here, you see that if you have sodium iron oxide, and also, if you have the end members like sodium manganese oxide, sodium iron oxide, you see that the rate capabilities for the solid solutions actually better. These materials are able to achieve higher capacity at faster C rates, at higher C rates. And one of the reasons for that is the suppression of cation migration. So we know from lithium-ion battery studies that manganese is quite mobile, right? It can move to an anti-site. You could have all sorts of site disorder within these manganese-based materials, and the inclusion of iron within the sodium iron manganese oxide compound is to really suppress that. It basically helps to stop the manganese ion from migrating to other sites. Okay, so you could see that here for sodium 2/3. So here you're not achieving stoichiometric ratios. So you have to have 2/3 of sodium ions in this layered cathode material. But at 4C, you're achieving a little bit over 50 milliamp hours per gram, whereas for the end members like sodium iron oxide, you already at 2C, you're achieving 30 something milliamp hour per gram. Okay, so the higher rate capability is really limited by the fact that having iron there will pin the metal oxygen ordering. Okay, so one of the issues with working this material that people have been trying to combat, of course, is that these materials are quite hygroscopic, and typically, you think, okay, well, can I just work in a dry room and dry this off? The issue is once you synthesize material, if it's out in the air and it's hygroscopic, not only will the H2O molecules adsorb, but they can also intercalate within the layers. So now if you're starting and if you're not appropriately drying off the material, then you're working with a compound that is not dry, right? So then sodiate upon desodiation and resodiation, you're dealing with sodium ions trying to compete with like intercalated H2O, right? So that's what, that's one. The other thing to note about this plot, if you look at the galvanostatic cycling, here voltage as a function of, well, doesn't really matter, capacity. But what you see is, unlike the layered materials of lithium-ion batteries, what differences do you see here that you don't see for the layered materials that we've talked about? Oh, what differences do you see in these galvanostatic cycling plots for the sodium ion cathode materials that you don't see for lithium ion batteries, particularly for layered materials? Oh, sorry. What's the intermediate range? I guess you can also be specific with your comparisons. Right.
Not like cathodes with voltage versus.
They have a slope throughout, yes, but that's also observed in lithium gold oxide, right? It's kind of slopey. Titanium disulfide as a layered lithium-ion battery material is also slopey-ish, right? And we concluded that that's because it's a solid solution. So, well, yeah, so there are some similarities. I guess you pointed out a similarity, but I'm also looking for contrasts. So not a contrast. Well, okay, I'll give you the slopey-ish. Sorry. Oh, voltage hysteresis. Okay. Sorry, did you say the hysteresis is large or small?
It's actually small.
This is smaller. Okay.
Not as much acid retention. So I'd say that
Yes. Although I have to say there's like caveats to all your answers. Yes, in general. Yeah. My question was also quite general, so it's hard to pinpoint, where exactly aiming for. Well, I was open to, all answers really. But I would say the caveat to that is sometimes you see, especially for the later, the papers that are, later than 1990, say, like say 2000. By that time, lithium batteries, you understand, you understand that, you have to tighten the voltage range and thus the available capacity, right? Like nobody cycles lithium cobalt oxide beyond, 60% of possible theoretical capacity, like you just don't de-interpolate all the way, right? So there you might not see as much hysteresis because it's already tightened up, because of that. So some of the plots that I've shown before have been from literature that's a little bit older, and thus I guess it skews your observations as well. What you see here is the existence of plateaus that you don't see in layered materials for lithium ion batteries, right? So you see here, there's sort of a plateau here, and yes, it does slope all the way through. So I guess what we really have to do is we have to sort of corral in our discussions and really tailor our arguments to a specific range of capacity. So what you see here that, is what we've seen in, let's say, lithium-ion battery cathodes that aren't layered, right? Like Mn2O4, we see the phase transformation jump, right? In the that arises, when we see the voltage jump there too. So what's happening is you see, there are phase transformations that are happening with the starting O3 structure or the starting P2 structure. So what that means is if there's going to be phase transformation, then we're going to have to deal with electrode material volume expansion and contraction, which usually results in deleterious phenomena like delamination and electrical conductivity decrease. So, the electrodes that you fabricated is now, not as robust as whatever you started off with, right? It's not touching the current collector as much. Your material is going to start fracturing. You're going to have a host of issues if you don't tighten up the voltage window and also limit the phase transformation. So already there's going to be, some engineering that we have to do with sodium-ion cathodes. I should also say before we go on to solid electrolytes, though, that here you see, and I try to sort of limit the conversation around layered materials, but what you also see are some similarities with that of lithium-ion vanadium phosphate, fluorinated phosphates that you see here with the sodium compounds. So you see the phosphates as well. You see the equivalent, phosphate base and also fluorinated phosphate based compounds. And so there's a lot of analogs that you can translate from lithium-ion batteries over to sodium-ion batteries, as in like fluorinating will also increase the voltage, so you can increase the power that way. So that's helpful. But what happens in these sodium-ion based compounds is you undergo, and all of them have the same issues, that you undergo certain phase transformations that you wouldn't have in lithium-ion batteries, lithium-ion battery cathodes. Okay. So I also wanted to talk about the differences, comparison of that of sodium-ion solid electrolytes with that of lithium-ion solid electrolytes, which we spent a lot of time talking about. So here you see the conductivity plot as a function of temperature. Well, here's reciprocal temperature, but here's temperature in centigrade. And so we talked about the beta double prime alumina sodium ion conductivity, and it's quite high. Now, with sodium ion solid electrolytes, what you'll see is a lot of work has been done in the thiophosphate based compounds. There's been a lot of literature, there's been a lot of work that's come out in the last 5 years on these type of compounds, right? And so there's been a lot of focus also on these thiophosphates, but also in improving their ion conductivity just by changing the crystal structure. So stabilizing a high temperature, high ion conductivity phase, but at lower temperature through either synthetic methods, and that we've seen with the lithium ion solid electrolytes as well, right? What we've done conventionally with solid state synthesis, people have tried to do, let's say, liquid phase or solution phase type synthesis to get these metastable structures that you wouldn't normally get. And when I say metastable, I mean, if you do conventional solid state syntheses, you access thermodynamic equilibrium phases that you can only get at higher temperatures. But now, if you want to get the high ion conductivity properties of those high temperature phases, but you want it at lower temperature, you have to then develop a different synthesis or some way of stabilizing these structures, right? And what we've seen for lithium ion solid electrolytes is just that. We've seen liquid phase synthesis with Li2S, 2S5, stirred in tetrahydrofuran. We've seen microwave assisted synthesis, basically rapidly heating. We've also seen quenching to arrest the metastable phase. So we can employ the same methodologies to that of sodium ion solid electrolytes as well to study their behavior and properties, but really try to correlate the structure to that of the properties that we observe. And there's a lot of interesting studies that have come out looking at how the local structure really dictates what you observe macroscopically in terms of the ionic conductivity. Okay, and so this plot shows, if here you see the tetragonal phase, and you can also have these glass ceramics, similarly to Li2S and P2S5, you can have Na2S and SiS2. You can have the Nasicon type materials that have been sintered as well. You can have these germanium-based compounds. Of course, the only issue with using germanium is the fact that it is so much more expensive than the use of silicon. And so while it certainly increases the ion conductivity within a certain temperature range, you run into the same issues of manufacturing and scaling up these types of materials. So sodium thiophosphate has been pursued pretty heavily because, of course, the elemental components are relatively inexpensive. So that's what I'll focus on. The focus of Na3PS4 has also been because we understand a lot about Li3PS4. But in terms of the sodium-based thiophosphate, right, in going from, let's say, sodium phosphate to sodium thiophosphate, you have the same advantages that you would have in lithium-ion solid electrolytes. So the sintering temperature is decreased, right? With what we've seen with the Garnet system, you have to sinter at very high temperature, like 1,000 C, maybe 1,200 C, at higher pressures. Whereas these sulfide-based compounds, you can do the sintering at lower temperatures and with less pressure, and sometimes maybe even cold sintering. While you apply the pressure. So there are advantages there. Now, the difference is at lower temperature, Na3PS4 has this tetragonal P-bar4 2C type structure. And what you see here is the lattice parameters are A is 6.952 angstrom, C is a little bit larger, it's 7.0757 angstrom. And you can see that the tetrahedra are a little bit skewed. So the sodium ions are in black and they're sitting in front of these tetrahedra of PS4. Okay, so but you can see it's a little bit tilted. And so that's the phosphorus in pink there. Now at the high temperature phase, you have the cubic structure, this I4 bar 3M structure, and you can see the lattice parameter is quite similar. I mean, it's really close when it comes to tetragonal and cubic. So you can imagine that the change is not going to be that difficult. I mean, you're going from 6.95 to 6.99. So it's a very subtle change. But now you have the ordered tetrahedra that you see there in blue that you don't see in, you see a little bit of the twisting in the tetragonal phase. Okay, so it's these subtle differences that result in large differences in the ionic conductivity at the end of the day. Okay, and so how do we tease that out? Well, we can do electrochemical measurements. Of course, we can also tie them in with materials characterization to really try to understand it. So this study, looking at the ion conductivity of Na3PS4, what you could see is if you do conventional solid state synthesis, right, you put in Na2S, you put in P2S5, and maybe a little sprinkling of phosphorus, a little sprinkling of sulfur, you get your Na3PS4. You can, but you'll get the tetragonal phase because that's the low temperature, that's this phase that will be stabilized at room temperature. Now, if you ball mill instead of doing solid state synthesis, so that's denoted as BM here, you can access the cubic phase, but at lower temperatures. Okay. Now, you can also ball mill the tetragonal phase, and then, you can also get the tetragonal phase by just annealing the ball mill cubic phase at like some gentle temperature, like 475 C is pretty gentle. Now, if you're working in solution phase synthesis, 475 C is actually quite high, but if you're in the solid state regime, that's actually quite low, and you're probably just like tickling the material a little bit. And in fact, you really are just doing that. It's 475 C at, for 20 minutes, which is a very short anneal time. In conventional solid state synthesis, you could be annealing for 24 hours, 48 hours, multiple days, multiple weeks even. So that's pretty, so you can control the crystal structure that you get at the end of the day by just changing up your synthesis method. You can also get smaller grain sizes by choosing an RP, depending on if you're doing high energy ball mill or planetary ball mill, but 500 RPM is pretty in between for about 48 hours, okay? And when I say high temperature solid state synthesis, getting this tetragonal phase, it's 500 C for 20 hours. So all of these synthetic conditions are actually quite mild when it comes to solid state synthesis. So what you see though is for the ion conductivity, loosely, I mean, this is the natural log of ion conductivity times temperature. But what you see is the activation energies are pretty similar, but the ion conductivity is increased when you go from the tetragonal phase to that of the ball mill cubic phase. That's achievable at lower temperatures, okay? And then when you anneal it to get to the tetragonal phase again from the ball milling, there's some deviation, but for the most part, it's pretty, they're similar. Okay, so one has to wonder, what is the origin? How do you have similar performance for tetragonal phase and also for a cubic phase when our underlying hypothesis was that the cubic phase has higher ion conductivity than that of the tetragonal phase? Okay, so clearly there is some similarity in the properties in the crystal structure of the material that's driving the ion conductivity to result in pretty similar numbers, right? If the claim is the average structure is one is cubic, the other is tetragonal, then they should result in different numbers. Okay. So that's when you, okay. Well, team, there seems to be a slide missing. I'll give you the punchline of the missing slide. The missing slide would have said that the local structure for that of the this cubic phase here looks like that of the tetragonal structure. So if you look at the sodium ion and its nearest neighbor, sulfur, what you'll see is that the local structure looks for the cubic and the tetragonal actually looks very similar, whereas the average structure is quite different. What we can do like X-ray diffraction and then do reflow refinement and look at the average structure and say, okay, well, one is clearly cubic and the other is tetragonal. But the local structure, when you sit on one sodium ion and you look at the nearest neighbor, the configuration there, they're quite similar. The cubic looks like that of the tetragonal. Okay, sorry, the ball mill cubic and the ball mill tetragonal looks like that. They look like each other, and thus they behave. The resulting ion conductivity that you can measure is the same. Okay. So that was the punchline. Although, yes. Mm-hmm. Yes. So, yeah. So that was a fascinating read because that once again is another data point that tells us we really need to look at the local structure. We need to not only look at the average structure for differences, but it's really the local structure that dictates what we observe macroscopically, right? So that's a pretty powerful statement for trying to engineer and design materials and go for, crystal structures that we thought, okay, would perform much better, or would perform, in a different way. So it's really, now the question becomes, how do we engineer new materials or new compositions, but have the same, like crystal structure of like higher performance that we would anticipate. So that's pretty exciting. Yes. Yeah.
When we're talking about the block crystal structure, it's now the light. The local structure.
The local structure of the ball mill tetragonal. Yes, although the ball mill tetragonal has been annealed from the ball mill cubic, whereas the high temperature solid state does not have that. So it's starting already from the cubic. So when you anneal, you have a different average structure, but the same local structure. At least that's what X-ray PDF seems to indicate. But I should say, one methodology should not be the standalone. So this was also looked at and cross-referenced with, I'm trying to remember, I believe it was solid state NMR, but there's also another one, I think it was Raman, I want to say. I'm trying to remember if there was also neutron PDF in there. But for sure, I think it was definitely wrong. So it was cross-referenced with two other characterization techniques well, we'll discuss in more detail when we come to materials characterization, but obviously I'll talk about it now in this context. It's sort of like, the elephant, analogy is depending on which part of the elephant you're looking at, you can have different interpretations of the elephant, right? And same thing for characterization and the length scales that one deals with, right? I mean, if you're looking at solid state NMR, you can determine like crystallinity, say, but you're looking at like nearest neighbor interactions, right? For solid state NMR. Now, okay, there's a lengthier description than this, but succinctly, solid state NMR can also give you a different picture than maybe what is like the entire picture, so there's that. And then you couple with that with, let's say, X-ray pair distribution function and also Raman spectroscopy, then you get a much better view of like the entire material. Because just looking at solid state NMR or just looking at Raman can really lead you down a path that is not representative of the whole compound, so of the whole material. So yeah, that's not a succinct description, but we'll dive into that when we talk about materials characterization, because there's been a lot of work done on, let's say, in situ TEM, which is really fascinating and really gives us insight into certain processes that happen, right at the, let's say, phase boundary layer or what have you, and that's really awesome. But is that representative of like the entire the thermodynamics of what is actually happening in the entire material? And often, if you're under a vacuum, the answer is no. So it takes a multitude of characterization techniques to really elucidate what's what's happening. Okay, that was tangential to the main point of that material compound. Now we talked about also for lithium ion battery solid electrolytes, we talked about disorder and how site defects can increase ionic conductivity. We also talked about widening the bottleneck, the diffusion pathway. So similarly, this has been done for sodium ion solid electrolytes as well. And so in this example, what you'll see is substitution on the sulfide site with that of the with selenide. And so you see here the what people have done is they'll introduce disorder via substitution of the phosphorus with silicon. So you see that here the solid solution you could see, or sorry, the glass ceramic. What you see is increased ion conductivity from Na3PS4 to that of the glass ceramic Na3PS4 mixed in with Na4SiS4. What you also see is if you mix in, let's say you leave the cation alone and you only mix in anion, what you see is ionic conductivity also increases as a function of how much selenium you put in. So here the so in terms of increasing this selenide content, that does increase the disorder, and you see the increase in ion conductivity. But typically, what you'll see also is what one has to consider is what we'll talk about next, which is the electrolyte interface. Typically, when we think, okay, well, you're increasing the disorder, that increases the intrinsic ion conductivity. But once you put it in a sodium or whatever metal or the high voltage cathode, then there's going to be decomposition at the interface. And depending on the substitution element, that's not always favorable. Because what you have to balance is, yes, the intrinsic ion conductivity might be increasing, but the thermal decomposition, the reducibility of the cation that you're putting in might actually have detrimental effects, as in inducing SEI and decomposition products that are not beneficial to transport of ions across the interface. And sometimes that actually is more important than just improving the ion conductivity. The electrochemical stability and the chemical stability of these compounds are also really important. So these fundamental studies are good in the sense that they provide a foundational understanding in how we manipulate the properties, but in terms of engineering the interface that is stable over the cycling of the batteries, that also has comes into play. And that's one of the reasons why our discussion of interfaces is going to be coupled all together in one module, as opposed to piecemeal with the introduction of different compounds. Okay, and what we've also seen for sodium ion solid electrolytes is what we've seen for lithium ion solid electrolytes as well, which is that if you have aliovalent substitution, you can also increase ion conductivity. And so that's what you see here in this particular example with Na3PS4 and introducing Na4SiS4. Now, there is a limit to the enhancement of the ion conductivity. So you do see increases as a function of increasing molar percent of how much you put in, and then you start to see a decrease. So there's usually a nice middle ground where you introduce, aliovalent substitution, you introduce disorder, but then after that, there's quite a bit of drop off with the end members. Okay. Now, you can't talk about phosphate-based solid electrolytes without talking about LGPS, but in terms of the sodium equivalent, we'll focus on Na2SN P2S12. right? So if you look at the ternary phase diagram, you could see that when you combine Na2S and Na4NS4 stable ternary compounds and Na3PS4, you get this this quaternary phase on the tie line. So it's a stable, thermodynamically equilibrium compound that you can access. And so you can see here the channels of sodium ions that can migrate, throughout the compound that can make it a fast ion conductor, which is really exciting. But instead of just substitution to increase ionic conductivity, you can also just process the material differently to increase ion conductivity. So here you could see that upon synthesis of this tin thiophosphate based sodium ion conductor, if you increase the cooling rate, so you basically just quench the material, you can modify the lattice parameter that results. Okay, so you can see here increasing of 2 theta degrees. So if you increase in Q, then decrease in Q, then your lattice parameter is increasing. Okay, so as your lattice parameter is increasing here, the conductivity is increasing. So processing alone can also control the ion conductivity, and you can see the change in twofold or two orders of magnitude more. So similarly, there are similar ways to manipulate the ion conductivity by just controlling the crystal structure that gets formed or the amount of disorder that is in the compound. All right. So the last little bit, which I think will start, but will not have time to complete, is the discussion of sodium ion battery anodes and how to design and process these materials so that you can increase capacity and also increase sodium ion diffusion. And so we talked a lot about graphite in lithium ion batteries. We talked about diffusion of lithium ions into graphite. Now, for sodium ions, there are some similar type materials in terms of the carbon-based families. So instead of dealing with graphite now, we're going to focus more on hard carbon, so disordered carbon. Obviously, hard carbon is a historical term for disordered carbon. Now, the lithium titanate, the titanate base family, you also see that here for sodium titanate base sodium ion battery anodes. There's also a number of conversion and alloying materials that you see for the anode that you've already seen for lithium ion batteries as well. So we'll focus on the hard carbon because a lot of work has been done there to try to understand how do we store sodium ions in these types of carbon materials, and then also how do we then change the microstructure and design these anodes so that they can store more sodium ions. Okay. And when we look back in history, I have to point out this paper by Rosalind Franklin, who really looked at hard carbon many, many moons ago. So you can see here, this is a 1951 paper, and it's titled Crystallite Growth in Graphitizing and Non-Graphitizing Carbons. So hard carbon is composed of carbon-based materials that are non-graphitizable. Okay, so the understanding of the structure, in fact, from X-ray diffraction, has been pioneered by Franklin, many decades ago. So she also worked on this while working on DNA. So that's pretty exciting. Yeah. Now, what you may have also seen in terms of the terminology, and it can be quite confusing, I think, when you're reading, especially older papers, there's a lot of references to hard carbon, but they've also been deemed as amorphous carbon, disordered carbon, non-organized. That was the first one I was digging up. The history of hard carbon, non-graphitic, we've seen that. Non-graphitizing, we've seen that as well. But generally it is carbon materials that have high mechanical hardness, hence hard carbon, that are non-graphitizable, right? And so that's different than that of graphite that we've talked about for lithium-ion battery materials, is because the sodium ions are larger, and thus, they have to be accommodated differently than just the use of graphite. Okay, so with that, I'm 1 minute over, so we will pick up here next time to talk about